Hello everyone, we're back for some more CRDT on differential data flow work. Now we had about 2 hours previously where we talked through this particular problem. I'm going to do a little bit of a recap and then I'm going to show you I did some tidying in your absence, and I'm going to talk through just a little bit of the tidying and then just sort of spell out where things go from here. There's not actually a lot of programming to do here, unfortunately. I've done most of it, but I am going to talk through what we've done and hopefully get you all up to speed on how the story winds down. At least I think by the end of this we'll probably be all done. Another thing that I learned is that when recording these videos, bouncing back and forth between the drawing and the typing is super annoying to edit afterwards. So I'm going to try to do it twice. Let's see if I can pull it off here twice. So just like at the beginning, we'll do a bit of a recap visually, then we'll scan through some code, and there'll be a moment where it'll be important to draw some pictures, I think. But I'm gonna try to cut down on that. If that's wrong, let me know. If you really like the pictures, and in particular you really like the pictures coming and going from the screen over and over again, that's the thing. But it's basically super hard to like scrub through and find those moments at which the editing on the iPad happens. It's just not flagged any useful way for me. Anyhow, with that all said, let's get started on some pictures. So here we are over in the picture drawing area of the screen. Very exciting. We're going to start with just a quick overview of what's going on in this CRDT thing. And for more context, definitely go check out this other video. But we reduce it down to, I think, a relatively, say simple problem, but like a relatively minimized problem, which is that someone has shown up with a tree of nodes. So there's these nodes, they have children. The children have siblings. Children may also have their own children, various whatever, sort of tree structures going all the way down. So edges going down and also siblings going across. There are a few other edges of interest. I'm going to try to change the color here, which are these edges going back up that are these sort of special edges from the last child back to their parent. And one of the things that we're going to try to do when given one of these big trees is produce the I just lost track of my blue color here. Take all of these edges, the down edges in particular, the across edges, put together all the down edges, all the across edges, and then find the edges that go up, these orange edges, up, and eventually turn into, at some point I'll learn how to use this. It's actually a really nice tool, better. Eventually go across here. So we're going to want to find these sequences of orange edges followed by their sibling edge that goes across. And that's our goal. Our goal is to take this picture, whatever it looks like, and turn it into a flat sequence of, there's the down edge, right edge. Who knows what's going on down here? Basically, a bunch of squiggle, followed by not 4 orange edges and then 1 blue edge, but just, if this is E or something, just that one edge. Sorry, I missed telling this story. If this goes to E, let's say, and this node down here is B, then we want to end up, our paths end at B, we want to take one final step to E, and continue on potentially. Whatever else is over here in the tree, we want to make sure that shows up afterwards. But the process is essentially unfolding this tree, which, we're doing a pre-order traversal. So every node, before we do its children, we visit the node, visit all of its children, and then unwind back up the tree in some tasteful way that collapses out these orange edges. So step one then. Step one, I mean, there are many little steps along the way, but step one in terms of hard things is collapse orange edges. Great. Step two, having done that, I'll use purple from this point on. Having done that, we have a bunch of edges that go left to right. We got them from this process, and some of the nodes have little X's, essentially little dead marks saying that I was deleted. And our next goal is to do some more collapsing, essentially. Take these sequences. They might not all be contiguous. Maybe this node is great, and this node is dead again. I'll have to put something after it, though. And we're going to want to replace this with all of the edges that go that don't involve a dead node. So this edge looks great, for example, this first one, gorgeous. But we're going to want to skip 1, 2, 3 nodes and put in an edge that hops over there. And then we'll need to skip this X and hop thusly. And continue on as appropriate. So this is some more collapsing. Essentially, we've got these longer paths of X's. We want to collapse those all down. And so we'll have step 2. We're going to collapse. I'm sure the right way to draw them, but these X edges, so edge going into X sorts of things. Collapse those down into a single edge. And that's most of the work. There's a bunch of other sort of attendant fiddling around with the data to make sure that we've got the right characters in the right places, or that we properly identify which nodes are children of other nodes and stuff like that. But this is the heart of it. All right, so we'll put this aside for the moment. Go back to the code over here, and I'm going to talk you through roughly where we ended up last time, at least in terms of the code that actually runs. I've reorganized it a little bit to try to be a bit clearer. It was initially sort of a monolith, and I've broken it up into some helpful methods. That's going to make it a bit easier for us to try out a few alternatives. So over here in the code, if we make that a little bit bigger and hide some stuff, we're going to start out with a fairly simple, just sort of main method here that is just going to start some things up, create some new input handles. I'm going to do something a little sneaky here, which we can discuss at some point if I remember. But essentially, I'm going to take all these identifiers that we had, which were a sequence number essentially and a user ID paired together, something that would be unique. And I'm going to hash all of them. And I'll try to explain why in a little bit. We could disable this. I've made all of the code generic in the type, so we don't have to do this. But there's a good reason to do this. We want to introduce a little bit of chaos into the identifiers for reasons that will become clear. But I did want to be clear that when we would start looking at performance measurements from this point on, technically the data is a little smaller than it used to be. We've reduced it down from pairs of 64-bit numbers to just 64-bit numbers. And the same answer comes out, so there weren't any hash collisions or anything like that, or ones of consequence, but that's a legit thing to worry about. So we invoke the RGA logic that there's just a method for it now. We'll be able to look at that without being bogged down by all this additional cruft. A little bit of stuff here about printing out the results. Essentially make sure we wait until we've got some results, print them out, that sort of thing, and hand back the input handles. So the way you build differential data flow is you create these new inputs. There are two things. One of them is a stream of data that can be used as a data flow, and the other is the handle that allows you to put data into that stream imperatively, which we then go and do here. This code is basically unchanged. And that's our little drivey harness thing, and we're not going to look at it again. Or I can't think of anything other than that randomness. There's nothing in there that's especially noteworthy. We're just going to instead drift down and start looking at this core RGA logic. And this is roughly the code that we had previously. You notice that I've made it generic with respect to two parameters, G and T. The G is the data flow graph. This is something that you have in all timely data flow computations. All of your streams only exist in the context of a data flow graph. They're not otherwise things you put in hash maps and sort of keep around forever. And the type that we're pushing around, this used to be a very specific type from the top of the file. This used to be an ID everywhere. And we just said, you know what, we'll do the whole logic not knowing much of anything about this type. We're going to have some constraints on it. It needs to implement hash for some reason. And it needs to be exchangeable by differential data flow. And that's just an important part of shuttling everything around. It also gives us equality and ordering. Those are sort of components of this composite trait. Great, so this could be generic with respect to whatever these node identifiers these are the nodes in the pictures we just looked at. So there's a bunch of logic here. I recommend swinging through the previous video if you want a slower walkthrough here. The only thing that I made some changes. I think they're largely not of consequence, but we can see. I put an explicit last child determination in here. Like we had previously figured this out using, some anti-join with next sibling to find children who didn't have a subsequent, and you could just pull the information directly out of the source. So I just did it more explicitly rather than a whole bunch of sort of fraught joins and stuff like that. We're pulling out, so essentially each parent has children. The children are in some order determined by the data. And we had to call out the first child for some reason. That reason being, I suppose, that as we go from the parent to a child, we want to follow the path to the first child. Those orange edges that we had, those are going to follow up the last child relations, though in the opposite order. I guess they're going to go from child to parent rather than parent to child. And although we had a bunch of complicated code before, we're going to think about this, I think, in a simpler way, which is say, we're going to take this last child relation, swing it around, so instead of from parent to child, it's child to parent, and we're going to think about trying to collapse this. And we'll get in a little bit to actually explicitly collapsing it, but just called this to collapse. And we had an iterative algorithm that would collapse these things, that would run through potentially a tree of folks pointing to other folks, acyclic tree, but so leaves pointing down towards the root essentially, and try to get everyone to point at their root. And this is basically the code that we wrote before. I'll show you in just a moment, but I've sort of popped it out so that we can swap around a few implementations a bit more easily. There's some related logic after the fact that we don't really want everyone along these. We really, when we collapse the orange path down, we want the starting node for that orange path, not everyone along the orange path. So there's some work to do to figure out who those folks are, and also once the orange path is finished, what do we stitch on to the end, right? We need to put that right-going next neighbor onto the end of the path as well. But we don't want to put them in the path, right? Because we might accidentally collapse. Like they might connect up to some more orange edges. We don't actually want to collapse that much. We just want to end up with one edge for each contiguous orange path. Great. And that got us to a point where we were able to spell out what is that sequence? What is the left to right sequence? So it's first child edges. There's the various next siblings that we're going to keep around, and then any substitutions that we might end up performing by virtue of sort of stealing a next sibling from a node that has children. Like any node that has children is going to point down to one of its children rather than to its next sibling. That next sibling will actually go to whatever its rightmost descendant ends up being. All right, so that got us through step one, the first collapse type, the collapse of the orange edges. The next thing we had to do is figure out what these x's are that cross out some of the nodes, and we're going to do some more collapsing, essentially. These blank steps, we're going to try to think about collapsing down. Those steps that go from who knows what through an x to some other node, we want to shrink those down into as small a path as possible and end up just with non-x follows an arrow to a non-x. So if all x's get collapsed out, that would be great. And we've got a little algorithm for that. This is a little bit smarter. It says let's start at value rather than starting at blanks. Like if we found all things that go through blanks and we had a list that was 13,000 long, which we did, we'd end up with 13,000 choose two paths. We don't really want that. So this is a little smarter and says let's start only from a value and move through blanks. We didn't quite get to this, so we didn't improve this at all. This the problem, if you recall from last time, was that 13,000 steps is too many. It's not too many. It gets done in about 2 seconds, but we can't parallelize it. It's overhead. It's all too bad. And we started on the process of fixing that for the orange path collapsing, and sort of got to a point at the end, which I'll summarize in just a moment when we look at the numbers. And then roughly we end. This stuff is just putting the symbols into the right place, and that's fine. We're not going to touch this over here. And I've got some code that follows. You can sort of see down here that this is all new stuff. We're going to toggle some of it on and off, so I've marked all of it as allow dead code because we're not using all of it at the moment. We are using collapse tree old, and this was the code that we got to. That said if you have a bunch of directed edges and they form a tree and you want everyone to ultimately point at their root, rather than walk one step at a time along the paths from the leaves to the root, which if the tree actually is a giant straight line, takes many, many iterations, you can do some more clever stuff where we essentially repeatedly double the lengths of the paths. So try to join two edges together, and then for every node of all of the paths that you might have found for it, keep the longest one. Subtract the length of the thing, keep the longest one. And this will eventually, folks will eventually start pointing at the root, and joins with those folks will point at the root, and everyone will eventually just stabilize that they're pointing at the root, because the root has, in this design at least, no outgoing edges. And, represents the longest path you can have because everyone eventually points to the root. This has some problems with it. I'm not sure if I'll spend too long explaining what those problems are. We'll see the running time is mediocre. And there's some more stuff down below, which I don't want to show you just yet. We'll get there. So let's look and see how this runs. This is a single thread. We're going to do a little bit of compiling. Unfortunately, there's going to be some compiling as we toggle in and out various implementations. I didn't want to go through and put a bunch of switch statements and give it additional arguments and make the recompilation easy. In part because I wanted to make sure I had a chance to talk through things rather than just hit you with a bunch of numbers. But all that we're going to see, hopefully, is our numbers pretty similar to what we saw at the end of the last episode. And just to give some context, when we started, things took about, on this computer, 2.3 seconds to run. And that was 1 worker, 2 workers, it started to get towards 4 and 8 workers, things just got slower, actually. So what we're seeing now is 5.3 seconds. That was roughly, I think, what we saw at the end of the last episode. This might be a little bit better because we hashed all of those pairs of integers down to just a single integer, so it's a little less state that we're keeping around. As we sort of walk around and do random access into things, it's about half as big. So that can make things a little bit faster. But, we're not super happy necessarily. We can run it with more workers, and I think a good thing does happen here, which is we made it go slower on a single thread, but the work was more parallelizable. And I think 4 is as good as it's going to get on my laptop. I did this on my desktop also, and things kept getting better with even more workers. But yeah, with only 4, I think, physical cores here, 4 is about as good as it gets. Now, so at some level this is good. We've changed the algorithm so that it responds better to multiple workers, though the big ambiguity at the end of the last session was it's not obvious they've actually gotten faster than what we started with. And if you're familiar with my takes on things, adding overhead that gets parallelized away isn't actually particularly helpful if all that you added was CRUD. Like if we just added a whole bunch of Bitcoin computation in parallel, we've made it a bunch slower, we've added more cores, and the actual computational essence didn't get done any faster. We just wasted a fair bit more time across multiple cores. So it's not deeply satisfying. And you might say, well, we lost, that sucks. I think in this case at least, different take is, we haven't done any of the optimization stuff yet. We haven't actually tried to make this good yet. And we'll do a little bit of that. There's also the point that the reason we added more work is because we went from an algorithm that did order n work to one that did order n log n work. And with a little bit of head scratching, and I'll show you, you can actually get an order n-ish algorithm for this problem. And we'll draw some pictures of that to make things, less unclear. I'm not sure if they'll actually end up perfectly clear. But let's talk first just a little bit about this algorithm, collapse tree, old algorithm, I guess, but code fragment, and possibly a variation on it that might be a little bit better. It's not going to be, both of these are going to have some core problems that they still do n log n work, and also that the work that they do is non-uniformly distributed across the workers, and that's going to be a problem too. So let's look back at the code here. What's going on here with our collapsed tree old? So someone shows up and gives us a bunch of edges, right? These are describe our tree, essentially, right? They point from some node to a parent, and then ultimately everyone all up to the root. Though actually it's important, this algorithm needs to work correctly if there are multiple trees. So I guess I set up here directed forest, and that's right, multiple trees. We don't know that they all go to one root. Each collection goes to some root, and our goal is to point all of the nodes at whichever root it is. Otherwise, right, we just look for a node that doesn't have any outgoing edges, must be the root, and point everyone at it. That's not right because there are multiple roots in here. And the actual challenge computationally is to figure out which nodes ultimately point to which of the roots, not, just find the root. That's a lot easier. So what happens, just to sort of recap what we said before, we're going to take all these edges and stick a length onto each of the edges. We're going to go from sources in the tree up initially one-step edges, but ultimately through ancestors, and keep track of the tree length, the number of edges we'll have to cross to go from any one node to an ancestor, and keep track of the maximum ones. So to do that, we take all of our source target pairs, and we're going to join them together. We need to do a little transposey thing here because we're looking for sort of a source to a via to a target. And that via is a source in one take on the edges and a target in another take on the edges. So we actually want the data indexed both by source and by target so that we can find pairs where source and target are equal. Right? So we can find a source that goes to a via and a via that goes to a target. And we'll do this thing here where we we just add their lengths together. We make sure to keep around the original option. Right, like if you're pointing at the root doesn't join with anything, so it's important to keep around the option of just keeping what you had before. We don't need to consolidate here because it's about to go into reduce. I'll just delete that. In principle, that makes the data a little bit better. The measurement's a little bit better, but it's not the core problem here. And then the reduce just says, sorry, I don't want to reveal too much about the next method. The reduce just says, go through each of these options. They're sorted because of the way we laid things out with the length first. They're going to be sorted, and so the longest of them will be the last one. Grab the last one and produce that as our output. Repeat, repeat, repeat until this stabilizes, and at the very end, go and just drop the length off. No one knows what this length is. We're not supposed to return a length up in the signature. So drop the length off, consolidate things, and call it a day. So nothing fundamentally wrong about this. There's some things we can clean up. This reduce, for example, it turns out isn't necessary, and we'll fix that in the next version down below. There's a thing that we're not going to clean up, which is too bad, which is this join map. When we think about what does this end up looking like, what are the arguments coming into the join map, this transpose and inner. Transpose in particular says we should index all of those edges by their destination. And in the limit, like towards the end of this iteration, all of the edges are going to point at, of a tree, are going to point at the root of the tree. So actually transpose is going to collect all of the edges in a particular tree at one worker. So if we had, and I don't know what we have in the data, but if we had one massive tree, for example, we put all the data just on one worker and say, you need to stick around and figure out where this connects to. Like these folks that are pointed at the root, where do they go next? Now, of course, they don't go anywhere next because there are no edges. But we still do all the work of putting all the data onto one worker and asking it, you should think really hard about these folks. And that ends up being a sort of disproportionate amount of work. It's not smooth across all the workers, and it is ultimately going to be a limit to scalability also. We'll get around this just by changing the algorithm. So, but interesting when you think about these operations to think, am I skewing the data by my interaction with it? And our iterative process absolutely was, right? It was absolutely making the destinations of all these edges much more skewed, basically looking like the roots of trees rather than nice uniformly distributed identifiers. on purpose. I mean, that was the goal of the algorithm, but we might have tried to design something a bit smarter that kept edges that were complete, like ones that have found a root and have stopped, and not feed them back into this part of the iterative computation. We're not going to go in that direction, but it's the same thing to think about. All right, here's a slightly different version of the same code that I wrote, and it's a lot simpler. Or, sorry, the data flow graph is less complicated. It uses some verbs that you might not be as familiar with. The spirit is very similar, that we're going to repeatedly join A, B, and B, C. It turns out we don't need to track lengths anymore. I'll try to explain why. Actually, the explanation isn't too complicated. When you join these two things together, since there's only going into each iteration one edge from A to B, it was the longest one, and one edge from B to C, the A to C edge that comes out is going to be the longest edge that you might have from A to C, so maybe we don't need to keep the length there. And the only thing you need to compare it against would be whatever edge you started with coming out of A, which was A to B. So if you find a C such that A to B to C exists, we don't need the A to B, it's worse. We should just delete the A to B. And if you don't find a C, A to B to C, you should just keep the A to B. And we don't need a reduce to figure out that logic. Like reduce will collect all the state together and potentially think really hard about it. And what we can do instead is much simpler, which is to say, and we'll see this in the logic down here, by default, keep whatever you started with. Right? If you got a bunch of A to B's, keep all of them by default. And now do your join, looking for A's to B's to C's. And if you find something, keep the A to B and keep the A to C and delete the A to B. And this is what we're going to do here. We're going to again do our transpose. We're going to do our join map with inner, and we're going to look for vias, sources and targets. And we'll keep the triple, the A to B to C, essentially source, via, and target. And then we're going to use this operator explode, which isn't a relational operator that you're familiar with, I'm sure. But it's a thing in differential data flow that lets you take whatever data you want and produce signed outputs. So outputs that have, plus ones or minus ones, it's going to be the exciting thing to do. So it can take a positive record and produce retractions as a result of it. And if you retract an input going to that, it'll flip the sign again and make sure to be correct and everything like that. So what this is going to say is when we see, this is the heart basic of this new approach. When we see a source via target produces output, the source to target with a plus one, keep that edge, that's exciting, and produce source to via with a minus one, delete that edge. And now when you sprinkle this into the mix of what do we have, so if we just concatenate this with inner, which is our loop variable, this will perform the task of forming the A to C edge and removing the A to B edge. And we didn't need a reduce for that, so that's nice. Explode is stateless. It just record by record applies these things. Consolidate takes a moment to add things up, but doesn't maintain any state over time. So this is cool. Let's try this out. Let's see if we can roughly remember how long these things took. 5.3 going down to 2.1 to 2.25. So let's wander back up, and I guess it's here. So this will take a different amount of time, and I assert that it will be better. I'm pretty sure it is, but it's not. We still have various problems. Just to skim back down, we still have the problem that in the limit, this collection, the transposed data collection, is still going to be a lot of people pointing at the root of a tree. That's not really fixed. We're still doing n log n-ish work. We're still doing this growing of all of these multiple edges coming out of each node over time. That ends up being n log n total work, more than what we were doing before. So it could be that this still isn't great. this is not so bad. So 1.9 seconds. So a few interesting things about that. It's faster than what we just saw with the previous bit of code, which was 2.1 to 2.25. It's also faster than what we started with. We started with 2.3 or so. I guess the previous code was also faster than that, but not quite as obviously. But we've changed the first digit here, which is amazing, even though it's a little 10% difference. Let's do some others. Let's see. So mostly we've just shaved off a little bit of fat, I would say. We haven't fundamentally rethought how to do any of these computations. So yeah, this is, I mean, that was previously 5.3-ish seconds and now 4.2-ish. So we shaved off a good amount of fat. We still have the problem, like that this is only the first of these steps, the orange edge collapsing step. We haven't done anything about the other step as well, so obviously we're not going to like magically make this be really fast. Though we have shaved off enough fat that we're actually able to with a straight face, be competitive with the prior single thread solution of 2.3-ish seconds that we were presenting. So that's good. This is one take you can have on how to make your code better, is just sort of go through and try to simplify the operators and make them as stateless as possible, because generally speaking, in differential data flow, these stateful operators are the things that get you, because you got to look at that historical state as well, and anything that you can just do the work, be done, and walk away is pretty fast. So, great, nlog-n algorithm. We're going to stop there with nlog-n algorithms. We're not going to delete these; they're actually still useful. You'll see in just a moment. But what we're going to do is consider a different class of algorithm. Sorry, actually, it's a very similar algorithm, but a different algorithm that will be useful for collapsing down these paths. And I'm going to start drawing some pictures again now. So let's look here. The main thing, and I've said this out loud, and I'll hint it. Okay, I'm just going to hint it in the code, even though I told you I was going to draw some pictures now. But we're going to move from collapsing trees, that's what we've done, to collapsing paths. Right, so trees can have multiple edges all pointing up to roots. And collapsing them makes total sense. Everyone should just point up at their root. There can be multiple trees, so you can have a super boring tree, but you can have multiple of these all in the same pile. We're going to switch now to paths, and it turns out that the task we have is actually collapsing paths, not trees. So the orange stuff is a path, not a tree. Paths are just trees where you have at most one child, right? So a path. Okay, I'm just going to draw a picture, but hopefully you're not, no other children dangling off of this thing, and we can still have our super boring one over here on the right side. This is an easier problem, or for me at least, it's easier, and we don't need to solve this general problem as trees, and it allows us to do some different algorithms that I think are pretty cool, and we'll talk about. So let me just draw a big path here, and we'll talk about trying to collapse it. So we've got a big path, and it goes on, let's say, forever, 13,000 steps, whatever it was in. So it's got a start S, and it's got an end E, and our goal is to produce something like S goes to E. Actually, we're not going to do entirely that. So it would be cool if we did S goes to E. What we're actually going to do is, can we produce a much shorter path starting from S and going to E? And that's what we're going to do. So how might we do this in parallel? If this is all we have to do is collapse these paths. We could borrow some of the previous ideas about, like, well, everyone along the way should start trying to find length 2 paths, length 1. But we can't actually, like, if we asked everyone to find a length 2 path, like, let's say this is A, this is B, this is C. If we asked everyone to start finding length 2 paths, like A would find A goes to C, and that's really cool. Should we collapse A goes to B goes to C into A goes to C? Like, let's say we've got this edge here. Should we just put that in? It's a little bit of a problem if B also found an edge to D, right? Because now we have A goes to C and B goes to D. And unless we're careful, we're going to end up doing something sort of silly and disconnecting the graph. So we do need to be a little bit careful, or alternately, we could just put all of these things in and increase the size of the graph by a lot. Basically, do all this repeated doubling that we've just done in previous steps. So we're not going to do that. We're going to do something else. Let's imagine that we were in luck and someone had alternately colored these nodes red and blue. I don't have a red and blue, but let's just imagine that someone has gone and done this so that maybe A is red, B is blue, C is red, D is blue. And we would take the blue nodes, potentially, like one algorithm would be sweet. In that case, let's just say filled in and not filled in. Perfect. Take the filled in nodes and connect their two endpoints. Right, so take the filled in this case, B, and say, yeah, we should collapse A goes to B goes to C into A goes to C. Ta-da, A goes to C. And we can feel comfortable doing this because we know that C is not going to get collapsed. Right? It's not going to get removed from the graph. All of the not filled in nodes will remain in the graph because we're only collapsing out filled in nodes. So if we go A goes to C, and also let's say C goes to E, oops, well, I guess that's the E then. It's not just the next letter in the alphabet, it's also the end of the thing. But if C to E was performed because D is filled in, we know that all of the not filled in nodes stick around, and so it's totally safe to do this collapsing. Now, and if we do that, we remove all of those filled in nodes, then we reduce the size of the graph by potentially a factor of 2 if half of them were filled in, but by the number of filled in nodes. And we can repeat the process again and again and again for as long as we can find filled in nodes. Basically, do this filling in or not of various nodes and repeating the process. And this takes, let's imagine we just did this. We're not going to do exactly this, but let's imagine we just did this until we got to S points to E. This would take a logarithmic number of rounds, and in total would do a linear amount of work, right? Because of the telescoping sum here, where if we're reducing by a factor of 2, then it's just twice the total amount of work. And yeah. No, we're not going to do that. We're going to do something very, 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 very similar. And let me just explain it the way we're actually going to do it. So let's imagine that instead of filled in and not filled in, every node has a number. So here's A goes to B goes to C. A, B, and C. And let's imagine, as we have already, that it's got a number which we're just going to treat as h of A, some hash of A, some hash of B, and some hash of C. And I just, as you saw in the code, went ahead and replaced all the node identifiers with a hash. So we're just going to use the node name itself. And now what we're gonna do in our version, not filled in or not nodes, is instead to say, let's look for B's that are the I think it's going to be the minimum. So like, let's collapse A goes to B goes to C if B is smaller than both A and C. Right. So B will essentially look at its two neighbors and say, oh, neat. If I'm smaller than both of you, I'll just excuse myself and replace myself with an A goes to C edge. This is safe for the same reasons the above is safe, which is that if B is smaller than C, so for B to excuse itself, A and C will stick around. They won't be removed by B, but they also won't be removed by any other edges because A won't look around and say, I'm smaller than B. It's certainly not smaller than B. So no matter what is leading into A, it won't remove itself. And C similarly will look around and say, well, I'm not less than B, so I won't remove myself either. The next node down might, of course, but... So this is a cute little trick that avoids any decentral coordination, right? We don't need to have someone come and alternately, color all these filled in and not nodes alternately. And we can just have everyone locally decide something about themselves using a hash function and look around. And this decentral coordination makes sure that we don't accidentally remove a node that will still be referenced by some other edge in the graph. Great. So that's the idea. We'll do this repeatedly. We'll do this both concurrently and repeatedly. So we've got D over here. It goes on, and it might be removed, or it might not be, right? Like maybe it turns out that D is actually bigger than C, and consequently, when D looks at C, it's like, well, I can't remove me, and that's a weakness, right? That's not going to be as good as having someone come and alternately number things for us, but it's potential cost. How likely are we to remove a node? So if we have, for every A goes to B goes to C, if we just think of this hash as sort of random and independent, and we just look at A goes to B goes to C for any node out there in the path, there is a probability 1 out of 3 that B is the smallest, as the smallest hash, right? So in expectation, the number of nodes we plan to delete will be 1/3 of the nodes. This is linearity of expectation. So we, the very first time at least, we're likely to, or we expect to remove 1/3 of the nodes. It's not as good as 1/2. 1/2 we could have done if we thought really, really, really hard ahead of time, but 1/3 is still, pretty solid. And then we're going to repeat the process, and you might be worried, and I'm not going to be able to reassure you too much here. You might be worried that the second time we do this, it's a little harder to reason about who's bigger or smaller. The identifiers aren't really random anymore. They're at least certain numbers because they have to be bigger than the B's. And there's almost certainly, I'm not going to do it, but almost certainly some analysis you could do about the principle of deferred decision here to say that, well, although A and C are both bigger than B, we don't really know much about which of the two of them is bigger than each other. So the relationship between them, which of A is bigger, which of C is bigger, is essentially as yet unresolved, and we could, in a sense, like flip the coin arbitrarily there. We're going to ignore that, to be totally honest. We're going to ignore that and just run the algorithm anyhow. The algorithm's correctness doesn't rely on P being roughly 1/3, just its performance. So that's good. This is a Las Vegas style randomized algorithm rather than a Monte Carlo style randomized algorithm, in the sense that we always get the right answer, but our performance depends on randomness, as opposed to potentially getting the wrong answer with some probability. But yeah, this is the code we're going to write. We'll take a look at it in just a moment, where every node has an identifier, this hash, and we're repeatedly going to look for pairs of edges, A's to B's to C's, that pass through the smallest identifier of A, B, and C, and then pop those edges out and repeat. I guess before we look at it, because the last little picture I want to draw is we started from some S on one side and came in some E on the other side. We don't want to erase those ever, and we're not gonna, because there's no edges coming in here, but they have a potentially naughty influence on the situation. If we're looking for the smallest folks to collapse, for example, and let's say S and E both have really small values, that'd be super bad luck, of course, right? But like H of S and H of E could be really small, and essentially they'll block collapsing their neighbors, right? So S and E, well, we certainly won't collapse anyone next to them if their identifiers are bigger than H of E or bigger than H of S. We will, and you can sort of reason this through, and if we take the max of H of S and H of E, we will collapse any nodes whose identifier is higher than that maximum out. They'll be gone. But we might get a little stuck next to the S's and the E's, and you can do a little bit of math here, or at least I did some napkin math, and you can sort of conclude that although this does happen, that we can get stuck here if someone else is, like if once their immediate neighbor, what's the right way to say this? Anyone bigger than S, smaller than S, sorry, anyone smaller than S will get collapsed out. And so we'll have a path that is collapsed out of S until we reach a node that is bigger than S. And I don't know, s's value is, let's say initially roughly halfway here or there. It won't take too many edges to find such a node. But now it's bigger than s. In fact, it's just some random number conditioned on being bigger than whatever s's value was. And we'll continue again until we find a number bigger than it, and then again until we find a number bigger than it. And initially that's fairly easy to do, right? It doesn't take very long to find that first person bigger than h of s. But as h of s creeps up, and each time it does creep up, it creeps up to some new random value halfway between the maximum value and the previous value. It gets harder and harder to find the next node with a higher identifier. And that means that we get longer and longer paths here as we come in from both sides, from S and from E. And morally what this turns into is that we should end up not necessarily with an S to E path, that would be super cool, just S to E, sorry, an S to E edge. But we do end up with an S to E path that is at most logarithmic in length. And that's going to be basically as far as we're going to get. We're going to stop there and say, great, let's just throw it back into our collapsing tree code. And that will that'll be good enough. We'll get the right answer, and we'll have reduced the 13,000 down to, I think in this case it's not like 13 or something like that. So let's just look at the code for doing that exciting collapsing stuff. This is collapse paths is the name that I'm given for it, and it's actually, you can sort of see it's not very big. The way in which we do this testing, looking for A goes to B goes to C, is surprisingly easy, or at least I think I made this hard first and then thought a little bit. But essentially, if we want to go from a large node to a small node, so if A goes to B, it needs to go from large to small nodes, yeah, let's just filter down our edges and say only keep the edges that go from large to small. And likewise, if we want to go from B to C, going up in identifiers, let's filter down our input edges, requiring that the source of the edge, the via, be less than the target. And now we have two sets of edges from large to small and small to large that are still in order, and we can just join them together. We can join them together once we spin the first ones around, so that the via is actually the join key. But we spin them around, and if we find a match, if we find an A goes to B goes to C, or B is less than A and B, we'll write them all down, of course, and let's do our explode trick again. All right. If we find this match, then we're going to delete both AB and BC and replace them with A goes to C. And that's exactly what this does. Here's A goes to C, the source to the target. And then we remove the source to the via, and we remove the via to the target. And essentially we're done. Like we mix back in all the original edges, because this is only the edit that we want to apply to those edges. Consolidate it up. It's important to have it consolidate at the end of your iterative stuff here, otherwise the algorithm will keep running as long as changes are occurring, and consolidates the thing that says, hold on, let's see if there actually were any changes. Let's add up the positives and negatives, and maybe it'll turn to a 0. That's the whole thing. It's not very complicated. It's certainly not very expensive. There's the join, and the join is actually on roughly half the data, not even the whole data twice. So we've actually reduced the state going to the join. And as a result, we're not actually going to get out all of the SDE paths, but we could we can nonetheless run one of these tree algorithms afterwards, and it should go a fair bit faster. We could have worked a lot harder and said, why don't we think about the S's and the E's, the starts and the ends, when we start, and make sure that they have really big numbers, right? I think big is good. Let's make sure that they have like the max values somehow, so that they never block anyone else's contraction. That will actually get us the SDE going out at the end. And you could totally do this. I don't know the relative costs of doing that work up front versus not. It's a more joining that's going on. And to be totally honest, this reduces the data enough that everything else seems like it's pretty trivial afterwards. So let's go back to our code, and we're going to uncomment this line here. This was where we were collapsing our last child relation. These are the orange edges, collapsing them down. And we're just going to throw in a collapse paths call here, the code that we just wrote. and rebind the same name. So this is just going to be this little optimistic bit of work we do that says, collapse down the orange paths as much as we can, because any amount that we do is not incorrect, as long as we don't overdo it. And then we just feed what's left into the logic we had before, which still calls into collapse tree new. And get rid of that. And down here, when we were doing those blank steps, right, we were going to collapse all those down using whatever this code is. And let's just do the same sort of thing here. We'll do a collapse paths on our blank steps as well, and then feed them into the iterative algorithm down below, and that's still going to be correct. So let's sorry, I'm hitting random buttons, hoping that there we go. Let's rerun this thing and see how long it takes with one worker thread. So the idea is that we've come up with this pretty cute iterative pre-processing in some sense on the paths. It could be the whole algorithm if we worked harder, but we're just using it as pre-processing. That is nice and parallel. It doesn't, as far as I understand, it doesn't cause the work to pile up at any one particular worker. It's a bit leaner in the sense that it's using sort of half the edges twice as opposed to all of the edges twice. And it does a linear amount of work. And it runs on one thread in 1.2 seconds. That's pretty cool. So in contrast, this is faster than we were getting on 4 threads in the previous algorithm. It's faster by almost a factor of 2 the single-threaded algorithm that we started with. And let's see what happens if we increase the worker count. All right, so it also appears that it scales relatively well, which is pretty handy. So this algorithm, this collapsing thing that we're doing now, collapsing of paths, scales really nice. Like all this work where we just look for small values of b that happen to be smaller than their neighbors, very nice and scalable. No one like that work is just distributed across workers by whatever b's name is, and it's not b being the root or anything like that. So the work doesn't get piled up in any particular location. Parallelizes nicely. It goes even faster on 8 cores on my desktop. Probably slows down at some point. I didn't get it to go too much faster than sort of in the 200 to 300 millisecond range. I think there are probably more things to start looking for in the program over here. There's, we've tidied up all of these loops that were going on. They were definitely the big pain in the butt first, but there's just other random, like we've got lots of random anti-joins and semi-joins with the same thing, and I don't know, like a lot of this could very likely be tidied up, not asymptotically reduced necessarily, but we could just thin out a bunch of the redundant work that's going on here. Try to do some of the clever things that Differential Dataflow supports with arrangements, for example. So rather than rearranging the data over and over again, let's take hasChild. Where's that? Yeah, it's just a collection, or sorry, it's the result of a distinct, which is just a collection. But if we made it into an arrangement, then we could use it twice without reforming an arrangement. Each of these, both semi-join and anti-join, will take hasChild and put it into an arranged data structure, index data structure. So we're just doing that twice for not a great reason. Also, like every node has children in this example. So they're all basically straight lines, right? So every node is part of this arrangement. We're building it twice. That's silly. We shouldn't do that. But I think I've shown you the thing that I wanted to show you, which is that although we started with, way back when, beginning of the last episode, we started with some algorithm that didn't improve its parallelization at all. It wasn't terrible in terms of running time, but didn't respond well to parallelization. We sort of dove in and found that there's basically a lot of sequential logic going on. All of these rounds of iteration that were 7,000 long or 13,000 long couldn't really be parallelized, at least not by Differential Dataflow. And instead, we had a little bit of a think and came up with a different algorithm, a few different algorithms actually, to try to make the work more parallelizable. And we started out with some slightly slower ones, good spirit, but constants matter and log terms matter and stuff like that. And then eventually got to the thing that I think is kind of cool, which is this collapse paths method. over here, and it does something pretty neat. It's specific, right? So it's only going to be good at collapsing paths. It really relies on the data only having paths in it. Like, we could give it a collection that contained tree-shaped data, and it would be wrong, right? It would do something crazy. As soon as it finds one match, it would remove that middle node, and then there's just a loose edge. The other child, which wasn't involved in that decision, is just like, well, where did my parent go? And that's just not going to be correct. So this was a change that I don't even know how to relate this back to data log, for example. There's the sort of path collapsing idiom that we were exploiting, though I'm not sure how easy it would be to look at the data log program and realize, this is only paths, don't sweat it. Like, there won't be trees here or anything like that. This is not appropriate for a general relation, and data log likely is, well, I don't know what data you're providing me, and I should only do correct things. We used some knowledge that was specific to the problem, right? Essentially, I think we can conclude for any input to this overall problem, this RGA CRDT, that the subproblem we arrived at, it does just have a path that we have to collapse, but I wouldn't want to be in charge of trying to figure out how to express that concept inside some data log engine. Not to say that you can't, or that you shouldn't think about that, but our lives were definitely made a lot easier here by being able to use some specific reasoning and sort of hotwire in our own implementation somewhere. We also, it really helped, and I don't know how this connects to data log either, but it really helped that we were able to express the concept of negative records, right? That we were able to describe rules that, I would say, invalidate certain facts. We don't actually need the facts to be false, but we do want to put them aside, right? We want to proceed forward not using certain facts. They're no longer relevant to us, and finding a way to communicate that to data log. It's not obvious to me, at least. You could start trying to put tags on facts to indicate in what rounds they're appropriate, but you don't want to have to retag. I don't know. It's not clear to me the right way to do this. So clearly we were able to get some mileage out of using some idioms that are not common to data log. It would be neat to see if they could be connected back, or it would be neat to see if data log is perhaps a very simple fragment on top of which, very simple fragment that could be on top of something like differential dataflow, which is potentially more expressive with retractions. And maybe in the same way that occasionally you peel back layers of abstraction to do things fast. You can do the same sort of thing here. But that's all I have for you. I hope this is sort of interesting. I'm certainly delighted to have gotten as far as some good running times. I've gone back already and filled in the data in the issue, and maybe we'll be able to close it soon. It's possible that you could go even further. I don't have any great asymptotic insights for how to take this down by an order of magnitude, but there might be some fun bit of tidying up to do. In any case, thanks very much, and I appreciate your time.